For months, you have been asking the same question. What are those joint weights attached to the main inlet valve? Why does the turbine shake during the startup? How does the turbine connect to the power grid? And most importantly, how do engineers safely start a machine that can generate nearly half a gigawatt of electricity? So today, I'm going through the entire startup process step by step. No complicated engineering language, just a simple explanation of what really happens when one of the world's largest machine comes to life. And I will be giving answers the mostly question asked in the comment section. Let's begin with this huge piece of equipment. It is called the main inlet valve. Think of it as the front door between the reservoir and the turbine. Okay, behind this valve is an enormous amount of water under pressure waiting for to flow towards the turbine. But many viewers keep asking about these large weights attached to the main inlet valve. What are they for? The answer is simple. These weights are part of a safety system. As long as everything is working normally, the valve stays open. But if electrical power is lost, hydraulic pressure disappears, or the control system fails, gravity takes over. The weight helps move the valve towards a safe position automatically. No electricity, no computers, no batteries, just gravity doing its job. It is one of the simplest and most reliable safety systems in the entire power plant. Okay, now the valve is open. The water path is ready. Everything looks prepared for startup, but the turbine still doesn't move. Why? Because before a giant machine can start spinning, it needs a little help first. Hidden beneath the turbine is a system most people never see. It is called the oil lifting system. The turbine, shaft, and the generator together weighs hundreds of tons. Starting all that weight directly on the bearing would create a lot of friction.
So engineer use this oil pump which delivers oils at 28 liter per minute with pressure of 13.7 megapascal.
This oil is pumped underneath the bearing surfaces. The pressure creates a very thin layer of oil that slightly lifts the rotating part. Think about an air hockey table. The puck doesn't become lighter, it simply glides more easily because it isn't rubbing directly against the surface. The same thing happens here. The joint machine is now floating on a thin film of oil and it's finally ready to turn. Okay, at this point water is ready. The shaft is supported by the oil system. All startup checks are completed, but the turbine is still standing still. That's because water has not yet been allowed into the runner. Now the governor system gives the command. Hydraulic cylinder slowly open the wicket gate. The movement is small, but even a small opening allows a large amount of water to enter. The water strikes the turbine blade at the correct angle, and then it happens. The turbine begins to move slowly at first, then faster and faster. hundred of tons of steel being rotating. The joint has taken its first breath. One of the most common question is, why is the turbine shaking? Is something wrong? Usually the answer is no. As the turbine speed up, it passes through a certain speed where vibration naturally increases. A simple example is a playground swing. If you push it just the right rhythm, the swing moves more and more. Sometimes similar happens in large rotating machines. Engineers know exactly where these vibration zones occur. The turbine passed through them quickly and continue accelerating. So while the shaking may look dramatic on camera, it's normally a planned and closely monitored part of the startup. And many viewers notice messages and alarms appearing on the control screen. At first glance, it can look like something is going wrong, but most of them aren't warning alarms. They are simple notification. The system is reporting that pumps have started, walls have moved, cooling systems are running, protection systems are active. Think think of it like a checklist. The plant is confirming that each part of the startup process is working correctly. Now the turbine is spinning at full speed, but it still isn't generating electricity for the grid. One final step remains: synchronization. Okay, before connecting, the generator must match the grid perfectly. I've told this already in many views, and I've also made a video on excitation system. If you want to look at it, you can check it here. Okay, this its speed, voltage, and timing must all be aligned. Imagine trying to jump into a moving merry-go-round. If your speed doesn't match, things won't go smoothly. The electricity grid works the same way. The control system carefully adjusts the turbine until everything matches perfectly. Then the circuit breaker closes. In a fraction of a second, the generator becomes connected to the national grid. The power can now begin flowing to home, business, and industries. Okay, one more question. How much power is 470 megawatt? People often hear 470 megawatt and wonder what that really means. A single 470 megawatt hydropower unit can produce about 630,000 horsepower. That's more power than hundreds of supercars combined. It all started with a surprising simple sequence. A valve open, a thin layer of oil lifts the machine, water begins to flow, the turbine starts turning, and the joint generator connects to the grid. So the next time you watch a turbine startup video, you will know exactly what you're looking at. You will see the safety ways protecting the turbine, the oil system helping hundreds of tons of being moving, the governor controlling water flow, the temporary vibration during acceleration, and the final connection to the power grid. What looks like a simple spinning shaft is actually a careful planned sequence involving thousands of parts working together.
Okay, one more thing. If you have noticed in the video that I have marked the red line, which was our initial position from where the Wicket gate ring started the movement, and the blue indicates that at full load how much the Wicket gate open or the cylinder move. You can see here with the help of these lines.